Okay, so welcome everyone to CO673 CS794 Optimization for Data Science. So this is our first lecture. And in this lecture, I'm going to introduce some course logistics. And I'm going to go over the course to give you a very brief review, give you some examples. Okay, so let's get started. This is an outline of the lecture. So as I said, we'll go over the logistics first. So I'm your instructor. My name is Yao, and you can reach me through this email here. And tentatively, I'm going to hold my office hour on Tuesday, 9 to 10 a.m. Eastern Time. So I hope this will work at least for most of you. If this office hour does not work for you, you can always reach me through my email and we can book a time. I will share the room link for the office hours on Piazza, so I didn't want to put it here. And we have one TA, tim.com, who you can reach through his email as well. So our course website is on my personal webpage, and I'm going to post all the slides or notes, assignments, including these videos on the course website. Okay, so you can always access all of this even though you're not enrolled. Okay, you're always welcome to access everything. We have a Piazza page, and this is mostly for people who are enrolled in the course. So you can discuss, you can post questions on Piazza. Me and Tim will try to answer your questions as fast as we can. But meantime, you guys can also discuss within each other, help each other. Okay, and all the announcements about the course will be made through Piazza. So make sure you sign to this page as well. And for the assignments, you need to submit your assignment through Learn, and your grades or solutions will be posted on Learn as well. Okay, I also want to mention that on the course webpage, I did put a time, namely Tuesday morning. So this is not the lecture time. Okay, so we're going to do asynchronous, meaning that I'm going to pre-record every lecture and I'm going to post the lecture to the course web page. Nevertheless, for formality, I still put a time for the course. This is mostly for you, so that you can reserve these times to study the course material. Okay, we are not going to meet during that time. Okay, so next, prerequisites. Formally, to really understand the things we're going to talk in this course, you need some basic linear algebra, multivariate calculus, and a bit of probability and statistics. Okay, so I'm going to review some of them throughout the course, but it will be very helpful if you can review what you have learned before, for linear algebra, calculus, and probability. I believe most of you, if you took a computer science degree or a math degree or stats degree or engineering degree, you must have learned linear algebra and multivariate calculus before. Okay, you just need to refresh your memory so that you will be more efficient in learning lectures in this course. We will also do quite a bit of programming in this course, because we want you to practice all the algorithms talk about. And we allow you to use two programming languages. One is Python and one is Julia. Okay, both of them are popular in data science. Python is the most dominating programming language in data science. So if you want to have a career in data science, you really must learn Python. Julia is a relatively new language that is very friendly and very easy to learn. Okay, so both of them are easy to learn. So even if you are new, you have not much programming experience before, you can still pick up the two languages fairly quickly by going through the tutorials on their website. Okay, and last but not least, we do expect you to have some mathematical maturity, meaning that you're not scared of proofs, you're not scared of reading equations. Okay, all right, so that is a prerequisite for this course. What to expect? So I want to make it clear that this is not a typical data science course or even a machine learning course. Okay, this is an optimization course, meaning that we're going to learn optimization algorithms. We're going to use machine learning models as a motivation to study these optimization algorithms, but we will not spend much time on machine learning. Okay, and this is a picture that I usually show in all my courses, right? We all know, computer science is cool, or statistics is cool if you're from statistics, or CNO is cool if you're from CNO. But at the end of the day, in most of these areas, we all have to do some math. Okay, so don't be scared of doing math. Okay, so I hope that's clear. Next, textbooks. And there will be no required textbooks, so you don't have to spend money on textbooks. We will be posting notes, slides, and videos on the course website. But if you want to learn more, okay, there are some fine textbooks for the algorithm that we talk about. So in particular, the two yellow books here, you can actually download through the university's library. Okay, and if you are new to programming, the second book here contains lots of examples in Julia. Okay, so you can actually practice by going through those examples. Okay, I want to repeat that you do not need to buy any of these books. Okay, but if you want to know more, you can. Work note. So roughly we're going to have 24 lectures, and each hopefully lasting for 30 to 45 minutes. This is shorter than a usual lecture simply because I'm talking non-stop, right? There's not much interaction between you and me, so this is why the video time is a little bit shorter than the usual class lecture time. And you should expect roughly 6 assignments, approximately 1 every 2 weeks, and each assignment will have 20 points. And at the end of the course, we are going to take the top 5 of your 6 assignments, and that will be your final grade. Okay, there will be no exam, there will be no project, you only need to do assignments, and we give you 1 free assignment just in case you have some errands to run throughout the course. We understand everybody may have difficulties, right? Okay, but on the other hand, because we are working from home, the important thing is to make small and constant progress every week. This is why we have, for formality reasons, we have lecture time on the course website. So you should try to reserve that time for studying the assignment for this course. Okay, do not wait until the very end, because you can easily be overwhelmed if you push everything to the last minute. And for assignments, as we said, you need to submit on Learn, and you can submit as many times as you like before the due date. Okay, we suggest you submit early and submit often. You don't have to wait until you finish everything. As long as you make some progress, submit. Don't wait until the last minute. In the past, we always have students, who didn't know the due date, or who made this or that mistake around the due date. I hope this time we will not have any of these incidents. Okay. Policy, and this is obvious, and typically I wouldn't spend much time on this, but from the spring term, it seems that because we're all working at home, and there had been a few issues. So I want to emphasize that you must do your work by yourself. Okay, you cannot copy any other student's work. You cannot copy answers from the internet. You're free to discuss with your classmates on Piazza. You're free to discuss with anyone else. You're even free to discuss with anyone on the internet. But you have to do everything by yourself. You have to explicitly acknowledge anyone or any source that helped you. Okay? We will not penalize you in any way if you explicitly acknowledge the help. On the other hand, if you failed to acknowledge and we found that maybe you borrowed or maybe you got hint from anyone or anywhere, that will be a serious offense. Okay, I want to be very firm on this, and if we find such issue, I will just hand this to the dean. Okay, I will not even deal with this myself. So please do your work independently and by yourself. Okay, there's no excuse, even at this difficult time. Okay, it's okay if you were late, or maybe if you didn't do well on one assignment, right? Because we gave you one free assignment. Please do your work by yourself. And we usually do not accept any late submissions. So a due date is a due date. All the due dates are listed on the course website. So at least you can anticipate, when you should submit, when you should finish a particular assignment. And of course, if you have, illness issues, or maybe you had a family emergency, feel free to send us a notice before the due date, and we can always try to accommodate that. Okay. And also keep in mind you have one free assignment. Okay. And after the marking, if there's any issue, you should appeal within 2 weeks after the marks are released. Okay. If you wait until the end of the course, we may not be able to come back and revisit any assignment. Okay, yeah, as you can see, we will be very serious about this policy. Okay, so that's all I want to say about the course logistics. And you should watch for your email if we have any further announcements through Piazza. It's always good to check your email at least once a day, or maybe once every other day. Okay. So now I'm going to give you a very quick overview of what's going to come. So this course is about optimization algorithms for data science or machine learning. And it should be obvious to you that machine learning really nowadays is everywhere. Right? In fact, every one of you use machine learning every day. Okay. For instance, when you open your mailbox, there is a machine learning algorithm behind your mailbox. Right? For instance, there may be an algorithm that detects if an email is a spam or not. Right? And every time you open Netflix, you're going to watch movies, and you will notice that Netflix will recommend new movies or new TVs to you from time to time, right? How does Netflix figure out which movie or TV it should recommend to you? Well, there's a machine learning algorithm that does that. And in fact, some of the algorithms we're going to study here are precisely the optimization algorithm that people use to solve these sort of recommendation problems. And on Facebook, of course, everybody is on Facebook or Twitter, I guess. And there's a recommendation problem there, right? And like who should be a friend, which tweet you should read, and so on and so forth. There's a search engine, right? Whenever you search, there is a machine learning algorithm behind that. And in fact, the algorithm we're going to study in this course are extremely important for search engines, because search engine has to deal with lots of web pages. And how can you have an algorithm that can scale to that amount of data, right? And of course, Siri, right? If you have your phone, or if you have an Android phone, I'm sure you have something similar. And how does Siri recognize your speech and do the recommendation, right? Amazon, similarly, what product Amazon should recommend to you. So all of these apps, they involve machine learning algorithm. And behind every machine learning algorithm, every machine learning model, there is an optimization algorithm. How do they actually solve the problem, right? And this is the focus of our course. And of course, there are lots of cool applications other than just the web applications. For instance, autonomous driving, bioinformatics, robotics, even finance, right? So machine learning really is everywhere, and every machine learning problem at the end of the day boils down to an optimization problem. Okay, and of course, it's also machine learning is also important for finding a job in data science, and I'm sure you know all that. So at the core of machine learning really is optimization, and this is our focus of in this course. Okay, we're going to talk about how to optimize machine learning algorithm or machine learning models. We're not going to spend much time on machine learning itself, but on the optimization aspect of machine learning. Okay, and of course, machine learning has many other aspects. For instance, it involves a lot of statistics, machine learning models, right? Like in a machine learning course, you'll learn more about models in machine learning. And there's also the system side, right? If you have an algorithm, how do you actually deploy the algorithm in a real system? And then there's also black magic in machine learning, like how do you tune parameters? Sometimes you have to do some hacks to make things work. We are to touch the optimization aspect in hopefully some rigorous manner, and also in some realistic manner, in the sense that you are going to implement some of these algorithms. Okay, so what you will learn in this course. First, we are going to study the basic theory and algorithms in machine learning. Okay, so we're going to give you a list of algorithms, and we're going to go through them one by one, understand, when they converge, what kind of problem can they solve, what is their convergence rate, and so on and so forth. And then you're going to gain some implementation experience, right? You're going to implement some of these algorithms, try them out, and hopefully have some first-hand experience. By the end, at the end of the course, I hope that you know when to use which algorithm, and you also know what guarantees these algorithms can give you. Okay, but eventually, I hope after this course, when you study other courses, or maybe you're doing a project, or maybe you find a job, I hope you to start to formulate your problem with algorithms in mind. By this I mean, typically we have an application, we want to solve some problem, right? And want to formulate that problem. And usually there is some flexibility in how we formulate our problem. And the important thing after this course you should keep in mind is that when you formulate your problem, think about what algorithm you can use to solve that formulation, right? And by doing that, you may actually formulate your problem in a way that is easier to solve in the end because you know what algorithm you can use. Okay, that should be your end goal. Okay, so this is sort of a rough or tentative outline of the course. So we are here at the introduction. So the first week really is the introduction, and in the next lecture I'm going to talk a little bit about some basics, like the basics of linear algebra, the basics of optimization. And then in the next few lectures we are going to talk about a bunch of gradient algorithms. These are all the variants of gradient algorithms that people use in machine learning. And after that, I'm going to show you one lower bound, meaning that what is the absolute optimum you can achieve with any gradient algorithm. Okay, and with that, we are going to talk about a technique called acceleration that can actually give you the optimal convergence rate under some conditions. And then we're going to talk about how can we exploit the structure of our problem to get better convergence rates. Okay, and after that we are going to talk about minimax problems. So these problems are gaining popularity now in machine learning, mostly because many problems we are interested in, they can always be reformulated as a minimax problem. And we're going to see some algorithms that you can use to solve minimax problems. I'll give you an example in a minute. And after that, we're going to talk about stochastic algorithms. Right? If you have a huge data set, how you cannot afford to go through the entire data set, what kind of algorithm can you use, and how can we reduce variance if we use these stochastic algorithms. Okay, and in the last week I'm going to talk something unusual. I put it here, the remaining gradient and maximum principle. So these are not as widely used as the other algorithms, but I hope that more people will use this as we learn more and more about them. Okay, so this is a rough sort of outline of the entire course. Of course, we may change things a little bit, maybe reshuffle things a little bit, but this is roughly what you should expect. And I will be posting slides, notes, and videos here, and you can see all the assignments, including the rough dates. This is when you should expect when we will post the assignments. And on the last column here, I'm also listing some machine learning applications that you can attack by using the corresponding algorithm. Okay, so we'll go through them later on. All right. So now I'm going to give you two examples in machine learning, okay, with the optimization algorithm that are related to this course. Okay, the first algorithm or model is called perceptron in machine learning. Okay, this is also the first algorithm I will talk about in the machine learning course. So what is a perceptron algorithm? It was first formulated by Rosenblatt in 1958. So it's an iterative algorithm, and this is typical for all the algorithms that we learn in this course. Okay, the algorithm we learn is always iterative. So you start with some point, and then you keep refining that point until some convergence criteria is met. So in the perceptron algorithm, you're given a data set. So xi, yi. So xi is usually called a feature vector. Yi is a label. So it's positive or negative. For instance, Positive may mean dogs, negative may mean the cats. Okay, so we want to distinguish dogs from the cats. And you have n of these data points. So n is usually what people say the size of the data set, and d is the dimension of the data set. So our goal is to find a line that can separate the positive from negative. Okay, and the perception algorithm can do that. It's extremely simple iterative algorithm. So you choose randomly or in whatever way you like a data point xi, yi, and then you test, is the current solution good enough? If the current solution is good on this training example, you don't do anything. Otherwise, you do an update. Okay, and the way you update is basically adding the training example to your weight to the solution you're trying to find. Okay, so it's okay if you don't get the algorithm here. Okay, this is just to show you how simple the algorithm can be. Okay, if you're going to implement the algorithm, it will probably cost you 3 or 4 lines, right? So the simplicity is what I want to illustrate here. Okay? Details do not matter for now. And to give you an example, so this is called the OR example. So this is a small data set here. This is basically our data set. You have 4 data points, right? So we have n equals 4 basically. And for each training example, you have 2. So d basically equals 2. And this OR here is basically your y. Okay, and let me change the 0 to -1. Okay, because it doesn't really matter. But -1 is more convenient for us. Okay, so you have 4 data points, and don't confuse this index here with the number of training examples. Okay, this is the index for the dimension, not the index for the number of training examples. Okay, that can be confusing if this is first time you see these vectors. I'm going to explain them in more detail in the next lecture. Now, just know that we have 4 data points, okay, and they are shown on the right figure. So we have 4 data points. The first data point has coordinate 0, 0, so it's here. Okay, and this data point has a y value -1, so this is why you see a minus over here. And the second data point is 1, 0, so the second point is here, it's a plus. The third data point is here, it's a plus, and the last data point is here, it's a plus. Okay, and our job is to separate the positive from the negative by finding a line. For example, the green line here can separate the positive from the negative, right? For instance, we can say everything above the line is positive, everything below the line is negative. Okay, so the perception algorithm's job is to find this green line or any of these lines. Okay, and it does so by starting with an arbitrary line. For instance, like an arbitrary line like this. It may or may not separate the positive from the negative, right? And then we're going to go through the data points. We're going to update this line iteratively, and eventually it will converge to a line that can separate the positive from the negative. So this is basically the perception algorithm, and all the algorithms we're going to discuss are essentially similar to the perception algorithm. Okay. So the perception algorithm, as I mentioned before, was basically the first AI or machine learning algorithm. And in fact, it is also an optimization algorithm. So if we will abstract this a little bit, basically the perception algorithm is trying to find weight vector W. This is basically the normal vector of the line you're trying to find. And B, which is basically the offset of the line you're trying to find, such that for every point we have this inequality. Okay, so this inequality basically means the true label yi, which is plus or minus, and this dot product here, they have the same sign. And the reason they have the same sign is because this dot product is basically what you can use to predict the label. Okay, so you want your prediction to coincide with the ground truth label. Okay, if you don't get the meaning of this, it's fine. All you need to know is perception is trying basically to solve this inequality. Okay, so it's an optimization problem. You want to solve a you want to solve an inequality. Okay, and perception does this by iteratively going through all the points xi, yi, one by one. Okay, and in fact, you can actually show the perception algorithm converges faster if, in some sense, the problem is easier. Okay, so I'm not going to give you the details here for that. So, but basically, this is what a machine learning course will do. Here, we're using the perception algorithm as an example for all the algorithms we're going to see. Okay, and if I'm going to abstract this a little more, basically, the perception algorithm tries to find a W that is in some solution set S. Okay, and as you're going to see, most times we're going to phrase our problem as a minimization problem or a minimax problem, but the algorithm we're going to study, they all boils down to this abstract problem. You're going to find a point in some solution set. Okay, all of these algorithms are doing this. The difference is, what do you mean by a solution set? Okay, so we are going to see this maybe in the next lecture and then throughout the course. Okay, so here's an example that maybe will illustrate what an iterative algorithm looks like using the perception algorithm as an example. Okay, so this is the OR problem, right? So we have the 4 points shown here, and imagine you start with a trivial solution, namely that you're going to predict everything as positive. So we're going to set W to 0 and B to 0, and the prediction is that you take W and you dot product with X and you add the bias and you take the sign of this. This is your prediction of the label. Okay, so when W is 0, B is 0, then it doesn't matter what X is, I'm always get 0 here, and then by definition sign of 0 is positive. Okay, so I'm going to predict everything as positive. But of course I will make a mistake on this point because this point is not positive, right? The true label is negative. So I make a mistake, then according to the perception algorithm, I will have to update W and B. Okay, and the way I update W and B is by adding Y multiply X to W and Y add to B. Okay, because X is 0, so I'm not going to change W, because B is minus, Y is minus, so B will change to -1. Okay, again I do the prediction, I realize now I'm predicting correctly on this point, but I'm predicting incorrectly on the other 3 points. So I'll keep running the algorithm. So we have 3 points that are incorrectly predicted. I'm going to choose one of them. I'm going to choose the red one. You can also choose the purple ones if you like. In fact, you can do this by yourself. Here I'm choosing the red one. So I'm going to do the update by adding YX to W and adding Y to B, right? If you add, now Y is actually +1, X is 1, 0. Now if you do the calculation, you're going to get to here, and now you realize this time now you are predicting correctly on the 3 incorrectly predict examples from the previous iteration, but again you're making a mistake on the origin. Okay, and then just keep running the algorithm because it's iterative. And then if you keep running, now you're going to make a mistake here on the y-axis, and then you update, you're going to make a mistake here again, and now eventually you're going to come to this solution. And now this solution shown in the green line here, okay, is shown here. So as you can see, it actually separates the positive from the negative now. The tricky thing is we actually have 2 points that are exactly on this line, right? And if you don't like that, you can actually keep iterating. Now, if you think I don't want any point to be exactly on the line, then you can take this point and keep updating. Now, if we take the orange one, then you keep updating, and then you keep updating. Eventually, you're going to arrive at this solution shown here in this green line. And this green line actually strictly separates the positive from the negative. Okay, so in other words, the perception algorithm has found a solution. So you can see on this simple data set with 4 points, it took us a while, right, to find a solution. But the nice thing is, these steps can be done automatically by the algorithm, right? If we go back to the perception algorithm, it's really simple to implement. Okay, you just let the algorithm iterate, and then eventually it will find a solution and return it to you. Okay, so I hope this shows you how an iterative algorithm works on a simple data set. Most algorithms we study, in fact, I think all algorithms we study are in this nature. Okay, so you should try to familiarize with this example. Maybe do the iterations by yourself. Maybe instead of going through this red, maybe go through one of these 2 purples and see what solution you end up with. Okay. Another interesting exercise for you to do is, what if we change one of the labels? Okay, if we change the point here from plus to minus, now the first thing you need to prove is that now there is no line that can separate the positive from the negative. There's no line that can separate the positive from the negative. But you want to, it's clear from the picture, but can you actually prove this? Okay, this is a very nice and simple exercise for you to do. Okay, in fact, I strongly recommend all of you to do this, because if you found this too difficult, then maybe you want to refresh your memory on linear algebra and calculus and how we actually do proofs in math. Okay. The other thing you can do is to run the perception algorithm on this data set, like what we did before. Okay, like what we did here. You can also run the perception algorithm on this data set when you actually know there's no solution. Would the perception algorithm behave crazily or not, right? You should actually run this by yourself and see what happens. Okay, this is a very nice exercise. Okay, so now comes the surprise. The perception algorithm was the first AI algorithm or machine learning algorithm, and it basically kicked off the entire field. But the interesting thing is, it was actually not even new, in the sense that there was another algorithm now called the projection algorithm for solving linear inequalities. Basically, if you want to solve this linear inequality system, then there's a very simple algorithm shown here. Okay, And you can see the similarity between this algorithm and the perception algorithm. And this algorithm was studied by Agamon and Moskvin and Schoenberg in 1954, whereas the perception algorithm was around the same time, even though they do not know each other's result. But if you go back, the citation we gave for Rosenblatt was in 1958. I think he started the work a little bit earlier than 1958, so it's around the same time. But this algorithm here is actually more general. Okay. Another nice thing about this algorithm is that they were actually published in the Canadian Journal of Mathematics. So I think this is another evidence that Canadians are extremely strong in AI and machine learning. Okay. So another interesting fact about this algorithm is, these people here are basically mathematicians, right? So they wrote the algorithm, and it probably got attention from another 4 or 5 people in the entire world, right? But if you look at the perception algorithm, which is essentially an even simpler version of this, the perception algorithm generated immense interest in society at large. Okay, so this was an article from New York Times in 1958. And this article was written because of Rosenblatt's work. Okay, so Rosenblatt was referenced here, and it said that the Levy revealed the embryo of an electronic computer, namely the perception algorithm, implemented in a computer. So the computer at that time was huge, right? That it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Okay, as you can see, this is quite exaggerating of the algorithm, right? Nothing has been achieved even today, right? But at the time, people were very enthusiastic about the perception algorithm. So the impact was enormous, and I think all of you, here, choosing to do data science, other than math, for instance, is another evidence, right? So there's a lot of impact you can generate if you come up with very good algorithms in data science. There's a book written by Minsky and Pepper on perception. In this book, they actually showed the XOR problem. Also, we give the example here. This is basically the XOR problem. It's going to show that perception cannot solve XOR problem. And this almost killed the entire AI field. But of course, later on, people realized it's actually quite easy to extend perception so that you can solve the XOR problem. Okay, that will not be the focus of this course. That will be a machine learning course. Here, my point is the perception algorithm is an optimization algorithm. It is a very simple optimization algorithm. You can easily implement it, and there are lots of variants. So most of the algorithms we study are basically extensions of the perception algorithm in one way or another. Okay, as we will see. And if you are more of a mathematical inclined person, there is also a very beautiful idea underlying the perception algorithm, namely that the algorithm is basically an implementation of the claim that the interior of the dual cone is not empty if and only if the interior of the dual cone intersects the original cone. Okay, for instance, in this example, we take 2 points, A1 and A2, and then we can generate the cone of A in this green cone, in this green area here. And you can compute the dual cone, which is the yellow area, okay, and the purple line is in the intersection of the two, okay. If you don't understand this, that's perfect fine. I don't expect any of you to understand this. My point is, there is a very beautiful math behind the perception algorithm. Okay, so if you want to sort of deeply understand things, you need some math to do that. Okay, so that is the perception algorithm. What's interesting is, I think I mentioned that earlier, that the perception algorithm converges faster if the problem is easier. So what do you mean by easier? Here is an example. So we have a data set here on the left, top left, and I have 2 negative points, I have 2 positive points, and I'm showing you 3 lines, right? The blue line, the green line, and the orange line. Each of them can separate the positive from the negative. Now, if I ask you to pick one, which one would you pick? Okay, I'll give you 1 minute to think about this. Out of the 3 lines, which one would you pick? Okay, just follow your hint, follow your hunt. Which one would you pick? I think most people, hopefully, will pick the orange one. It feels like the orange one separates them more, right, in some sense. And you can actually justify this by the following. So for each point, you can compute its distance to the line you pick. Like for instance, if I pick the orange line, this is the distance I can compute. I have 4 points, so I have 4 distances I can compute. And then I'm going to take the minimum distance. Okay, out of distances, I'm going to pick the minimum one. For instance, this is probably the minimum one. Right, for each line, I can do this. And I'm going to compare different lines based on the minimum distance. Okay, for instance, if you pick the blue line, then the minimum distance could be this, is shorter. Okay, and this is how we decide which line is better. And if I formalize this, essentially we're trying to find a line parameterized by this W, and we're going to find W by computing the minimum distance to every point, every training point, every xi, yi. Okay, this is the minimum distance. It's okay if you don't understand why this is a minimum distance. I'm telling you it is. We're going to see this later on. And I want to maximize this minimum distance. Right? I want to find a line where this minimum distance is largest. Okay? And this gives you basically a minimax problem. In this case, it's a max-min problem. Okay, so we're going to spend quite a few lectures on how do we actually solve these type of problems. And as I mentioned before, these problems are quite popular now because, for instance, in generative adversarial networks, in reinforcement learning, in adversarial examples, all these hot topics, they essentially boil down to solving a minimax problem. Okay? And the other interesting thing is, once you have a minimax problem, sometimes you can actually switch the ordering. Okay? In this case, if you switch the ordering, then you can actually get a different formulation, and you can actually have a different algorithm where basically what you do is, for the negative examples, you just compute the convex hull of the negative examples. If you don't know what do I mean by convex hull, we're going to explain in the next lecture. For now, just say we just connect the 2 negative points. For the positive points, you do the same thing. Okay? And then you find the shortest pair on the 2 lines. Okay? The shortest pair is here. And then you find the bisector to the shortest pair. That gives you the optimum, or the sort of the best hyperplane biased line that can separate the positive from negative. Okay? And now comes the interesting fact. this line here is the solution to the so-called support vector machines. And the distance here basically characterizes how difficult or how easy this data set is. The bigger this distance is, the easier the data set is. And if you run perceptron, the faster it converges. Okay? So in some sense, support vector machines, perceptron, they're related to each other. The difference is, in perceptron, we just run the iterative algorithm and we arrive at any solution that can separate the positive from the negative. Whereas in support vector machines, you actually find z separating hyperplane, or the z line that separate the positive from the negative the most in some way, in some sense. Okay, so the right figure shows you that you really have to take the convex hull. You cannot just compare the pairs of training examples. Okay, so we see that in some machine learning models you have to solve a minimax problem. Okay, and we'll see how to do that. And if we want to generalize this even further, what happens if there's no line that can separate the positive from negative? Then you can do the so-called empirical risk minimization, where basically you have a loss function and you have a regularizer. This is typical for most machine learning models. And depending on what loss function you pick, you have to use a different algorithm. For example, if you pick L to be the logistic loss, then you get basically the so-called logistic regression in machine learning. And then you can actually use Newton's algorithm because this loss is very smooth, as we'll see later. And if you use the hinge loss in red, that's basically the support vector machines. And the difficulty is the red curve is not differentiable at this point. Then you have to use a different algorithm to do that. Okay, and because of this term, like what norm should you put here, it also affects what algorithm you should use to solve this problem. Okay, so we'll actually study a variety of these and then you're going to apply them. Alright, so that's basically my first example, the perceptron algorithm, which happens to be the first AI algorithm or machine learning algorithm. But it's also an optimization algorithm. Okay, now I'm going to give you another example which is quite recent, and it also relies on lots of algorithms that we are going to study in this course. So adversarial example. So what is adversarial example? So imagine you have built a machine learning model. In this case, it's a neural network, but really it can be any model, right? And the model works as follows. So you take an input. In this case, it's an image. It's a dog image, right? So you give this input to your machine learning algorithm or machine learning model, and the machine learning model will do the computation, and then at the end of the computation, it will spit out a prediction, right? In this example, we want to distinguish what kind of breed the dog belongs to. So for instance, if we have a very accurate machine learning model, it will predict the input image is a Shetland, right? So this is a breed of the dog, which is correct in this case. So now, given that you already have a very accurate machine learning model, an adversarial example is where we try to attack the model. Okay, so what I'm going to do is I'm going to take the original input where the algorithm, the machine learning model actually predicted correctly, right? I'm going to slightly perturb the input image. So I generate this noise, and then I'm going to add to the original input image. I'm going to get a slightly different image, right? For a human being, this is still a dog, the same dog, the shetland. I should predict shetland, right? And the interesting thing is, if you give this image to this very accurate neural network model, it will actually predict it's a collie, which is a different breed of dogs. Okay, so in other words, we have managed to fool the machine learning model. And the difficulty here, of course, is how do you construct this noise that does not change the appearance of the input image, but nevertheless for the network to make a different prediction, right? So we want to actually compute this perturbation here. How do we compute this perturbation? And that can be formulated as an optimization problem, and you can actually use the algorithm we learn in this course to solve that optimization problem. Okay, so let's make this a little bit formal so that you know what's to come in this course. So we have a neural network. So we're going to abstract the neural network as a function that takes the input x, and this neural network has parameters of its own w. These w basically are these connections here, shown here. Okay, for us, in this example, w is fixed, x is the input. Okay, in typical machine learning course, you are going to actually find this w. Okay, here we are assuming w is already given to you. You're not going to change w. You cannot change w. It's given to you. And x is the input, as we mentioned. W are the weights of the network. And we're going to predict the breed of the dog. So this is our label, y. Our job is to perturb the input image x by adding a perturbation delta, right? So I'm going to get x tilde as the perturbed input image. And what I want to do in adversarial examples is to find this perturbation, right? I want to find a perturbation in as small as possible because I don't want to change the input image much, right? I want to find a small perturbation such that after I perturb the image now, the network will make a different prediction, will make a wrong prediction. I want to fool the network by adding the minimum amount of perturbation, right? So this can be formalized as the following. If you want to solve this, you can say maximize this subject to, the perturbation is small. And the important thing here is, remember, when you train a machine learning model, what you do is actually minimize this function by tuning w. Okay, x is fixed, there's no delta, x is fixed, you're minimizing this function by tuning w. Now if you want to fool the network, because this is how the network was trained, you're going to do the opposite, right? You're going to perturb the input x by maximizing that function now. Okay, you're going to do the opposite to fool the network. It's very natural to do that. And once you formulate the problem this way, now it's an optimization problem now, and you can apply many optimization algorithms. Okay, in particular, you can apply, for instance, the projected gradient algorithm. You can apply the conditional gradient algorithm. You can apply a splitting algorithm here. Okay, these are different algorithms. And in this example, what I'm showing you, as you can see, this is the perturbation. You can only perturb the image up to this amount. And in some of these algorithms, they actually apply the so-called smoothing idea. So we'll talk about that in detail later on. For now, it's just a parameter, okay? And you can see some of these perturbations, they were not able to change the prediction. Whereas some of the perturbations, some of these algorithms or perturbations they produce, they were able to change the prediction. Okay, so this tells you different algorithms they may work differently on the same problem. Okay, so you really have to choose a suitable algorithm in order to solve this your problem. The other interesting artifact here was that because we did smoothing in these three algorithms, as you can see, if the smoothing is applied and the smoothing factor is big, then you actually the noise you produce, like here for instance, they will actually reflect the shape of the input image. Okay, that was an artifact. In fact, if you use a different better algorithm, you do not see this artifact. Okay, so we've talked about this, and the interesting thing is you are going to actually learn the algorithms that we used in this work. So here's pictures for people who are not familiar with dogs like me. We said that is a Shetland, there's a collie. These dogs, I believe, are Shetland, and the dogs below, they are collie. Okay, as you can see, they are quite different. I think a human would have no difficulty to distinguish them. And yet, after this perturbation, this dog here, the machine learning model will actually predict it to be a collie instead of a Shetland. Okay, so to give you an idea, the two algorithms above are basically the projected gradient algorithm and conditional algorithm. We're going to cover them in lecture 3 and lecture 6. The bottom algorithm here involves smoothing, the parameter gamma, and splitting as well. So we're going to cover them in lecture 11, lecture 13. And last but not least, if you want to make your machine learning model more robust, right? One way to do this is by constructing these adversarial examples and then put them back to retrain your machine learning model. That essentially is a minimax problem, and we're going to talk about that in lecture 14 and lecture 15. Okay, this is just an example where I'm showing you that even for one sort of application in machine learning, we are going to need quite a few algorithms from this course. Okay, so this is why we're going through a lot of algorithms, because if you want to do work in data science, sometimes you have to use a bunch of them in order to achieve your goal. Okay, so that's the two examples I want to give you details on, and I'm going to quickly go over some other examples. So this is another one where you're given an input image. This is the original image, and then maybe what you can get is a noisy one, right? It's not the ground truth image, and based on the noisy image, maybe you want to recover the original image. Okay, and this is one recovery here, and this can be written as an optimization problem where x is the y is the image that's given to you, and you want to find a denoised image x, and this term here measures the closeness between the input and the denoised version. And this is the regularization where we want the denoised image to have some certain properties. Okay, and how do we solve this problem? You can actually solve this using an optimal algorithm, as we'll see. Okay, this is another application or another area where we need optimization. And this is a data set on the right. I'm showing you a data set which where we basically recorded the number of phone calls in Belgium during the years from 1950 to 1975. And the interesting was there was a sharp jump around 1964. And then a few years later, there's a sharp decrease around 1970. The reason this happened was because that during 1964, so the Belgian government, they upgraded their device for recording the number of phone calls, but they made a mistake. So instead of recording the number of phone calls, they actually recorded the total duration time of phone calls. Okay, this is why you see a sharp increase. And then a few years later, of course, they realized the mistake and they fixed it, and everything went back to normal. Okay, so this happens a lot in reality. When you connect your data set, there's a lot of measurement error, there's a lot of human error, right? It's inevitable that your data set has outliers. So, but if you're not careful, when you fit your data, you may be heavily influenced by these outliers. For example, if you do linear regression, namely fitting a line to these dots, you will get this blue line here. Okay, and it's heavily influenced by these outliers. On the other hand, if you do a more robust regression algorithm, it's barely affected by the outliers. Okay, and in fact, even now, if you ask an average data scientist, if you give them a data set and if you ask them to fit a line, most of them will choose to use linear regression. That is not robust. And the reason most of them will choose linear regression is simply because linear regression is easy to solve. Right? We know how to solve linear regression. But if you change linear regression to something different, for instance, if you change to absolute deviation, namely that you minimize the L1 loss instead of the L2, and because minimizing the L1 loss is much harder than minimizing the L2 loss, so most people will just not choose that, right? But hopefully, after taking this course, you will solve that problem. You will be the few who can actually use robust regression algorithm. Okay. Here's an example to show you if you use L1, namely the absolute value function in black, it's not differentiable here. This is the difficulty. How do we deal with this non-differentiability? We're going to have algorithms that can deal with that. We can also smooth the loss function. This is the smoothing that we're going to talk about later on in the course. The interesting thing is nowadays in neural network training, many people actually use this smoothing idea without even knowing it. Okay, so I'll explain what I mean when we talk about smoothing in lecture 13, I believe, or maybe 11. Okay, so a little history about optimization. So this is a quote from Leonhard Euler, and he basically believed that nothing in the world takes place without optimization. And there is no doubt that all aspects of the world that have a rational basis can be explained by optimization methods. I cannot agree more with this. So it doesn't matter what you do, right? At the end of the day, you're going to optimize something. And you're going to need algorithms for that purpose. Okay? And if you work in data science, you're going to deal with a huge amount of data. And you can only use algorithms that can scale to that amount of data. That is the focus of this course. Okay? In particular, we're going to study lots of variants of the gradient algorithm that goes back to Cauchy. Okay, so many of you who took your calculus course, you might remember that there are limits, there's a continuity, right? All of these notions are due to Cauchy. But he also invented or discovered the first gradient algorithm when he was studying the orbits of planets. Right? He needed to solve some nonlinear equations, and he used gradient descent for that purpose. And we're going to talk about gradient descent starting the third lecture. Okay, so this is my last slide where I want to convince you that there is no algorithm that can work for every problem. Okay, in fact, you can actually formalize this. There is a theorem due to Warpert and McReady that basically says no algorithm is better than any other algorithm when you average their performance over all problems. So what is the implication of this statement? A, you shouldn't try to solve all problems, right? You should always try to focus on one or maybe one class of problems at a time. And you really need to exploit the structure in your problem, right? And by exploiting your structure, some algorithm may behave much better than other algorithms. So you need to know your problem and you need to know the algorithm, right? What algorithm can you use for what kind of problems? And you should also try to know what are the alternative algorithms, right? What is the best possible algorithm I can have for this particular problem? Okay. And also, last but not least, you should always try to be open to the impossible, because every theorem, every statement, behind every theorem or every statement, there's an assumption, right? Maybe that assumption makes sense for your problem, maybe that assumption does not make sense for you. You need to decide when it makes sense, when it does not, and when it does not make sense, then maybe you can do the impossible by, breaking the assumption. Okay. All right. So that's all I want to say in this introductory lecture. As I mentioned, I did, talk a few about the machine learning models. We saw a few equations. It's fine at this stage if you don't understand any of these equations, because this is an introductory lecture. I wanted to give you a feel of what the course would look like down the road. So in the remaining lecture, in the next lecture, in fact, I will go through some basic linear algebra to familiarize you with the notations and some basic optimization techniques. And starting from lecture 3, we're going to study algorithms and analyze them, and you're going to implement them as well. Okay, so thank you for listening. I'll see you next time.